Now we'll begin our next section of the class, and we are taking a little bit of a journey through the history of science up to Isaac Newton. And we've got to understand one important part of this history, which is that one of the most important driving factors in the history of science is the observation of the heavenly bodies. This can't be overestimated. In other words, the ability to see the night sky and to see the planets and the stars and their motions in the heavens has been a key factor in the development of physics and the development of science. And here we have we've got a diagram of the ancient Ptolemaic system. Now, Ptolemy was a Greek, an ancient Greek. He lived around 100 BC, and he recorded the movements of the planets, and the understanding at this time was a geocentric universe. And geo means earth, centric means center, so earth-centered. So you see here in this drawing, we've got the earth in the very center of this system. And if the earth is in the center, and you graph the movements of the planets in the sky over the course of a year, you get a very strange pattern, which is you get these epicycles. So the planet will appear one night to be in one position, and then it will kind of go backwards and make some kind of crazy orbit and do all these wild things. And what you're really seeing is the interference of the fact that the orbits take different times to go around the sun. But of course they believed the Earth was in the center, so they had to draw the solar system and the movements of the planets as if the Earth was in the center, and you got these crazy, inexplicable epicycles. So again, nothing really happened with this for about 1500 years, but then came along a fellow by the name of Nicholas Copernicus. So Copernicus realized simply that if you took the astronomical observations and instead of having the Earth in the center, you put the sun in the center, as we see here, the sun is in the center. Then instead of having all those epicycles and strangeness, you end up with a very simple model of the solar system. Now, this is an important principle in science, which is that if your theory makes your observations make sense in a very simple way, that means it's a powerful theory and likely to be correct. So this was the first time that a theory like this had been devised that basically took a whole lot of observations and put them all together into one very neat, coherent package. Of course, this was a big deal at the time, in the sense that having the Earth in the center was not just a scientific idea that people had, but it was also part of their religious worldview. They connected the idea of an Earth-centered universe with the centrality of man, or the importance of man to God, and they simply assumed that if men and our lives were important to God, then the Earth must be in the center. But again, this is just an assumption, and it doesn't necessarily follow that the Earth is in the center. So this Copernican revolution, as it was called, Copernicus's new model of the solar system, was very controversial. But it sparked a resurgence in science. And so we'll follow what happened with Copernicus up to Isaac Newton. Following Copernicus, we have Johann Kepler, and Kepler proved, in a sense, Copernicus's theory of the the heliocentric or sun-centered, helio being sun, sun-centered orbital mechanics. So Kepler took up Copernicus's cause, and by the time Kepler came around, other astronomers had made very detailed observations of the heavens. So now it was known not only that the planets, more was known about the orbits of the planets. For example, it was understood at this point from observation that they were actually ellipses or ovals, not circles, not perfect circles. So Kepler he became very famous, first of all, for his laws of planetary motion, which we see over here. I'm trying to here's the pointer. We'll learn more about this later in the class, but basically, it has to do with the relationship between the ellipse of the orbit and the speed of the planet as it goes around the sun. So Kepler figured out all those laws of planetary motion, and he made other contributions that started to basically seal the deal that Copernicus was correct. Now, here's the interesting thing to keep in mind. Kepler had no theory as to why it would be a sun-centered system. It just made the most sense from the observations that it was a sun-centered system. And he was able to come up with these laws of planetary motion that held true for all the planets and made sense in terms of their elliptical mathematics. So one thing that was not so scientific about Kepler was that he believed the orbits were contained in perfect solids, the perfect solids of Plato. And again, I'm trying to get my mouse to appear. Here it is. So this is what this diagram here is. Now, he didn't believe that these solids existed in outer space, but rather he believed that the orbits were spaced at the distances they were spaced because they would fit inside of a given Platonic solid, which are these mathematical forms nested one within another. And this isn't a strictly scientific idea. It's more like numerology or astrology or something like that, in that there's no causal relationship between these shapes and the distances of the orbits. However, he is touching on something important, which is that all of these scientists believed that there was an underlying order to nature. But the question is, how does that order manifest itself? And this gets into a whole discussion of what it means to say that nature even has laws. And this is another discussion which we'll have at some point, not right now. But Kepler essentially had this idea that nature is ordered, has some ordering principle, and so therefore, if it has an ordering principle, it might as well be these perfect solids, or Platonic solids, that have very regular geometrical properties. Of course, the orbits aren't defined by these solids. However, there are ordering principles in nature which are very powerful. It just happens to not be this one. So again, it's the thought that counts. He's on the right track, but maybe taking things too literally. But again, it's a step. These are all steps towards a scientific synthesis. So now we'll go from Kepler